So now in question number 9, we are asked to expand the logarithm rules and let log x equal a, log b equal y, log y equal b, and we let log z equal c. So given these three substitutions for these values, we are asked to find or express the following identities in terms of a, b, and c. So express it in these terms. So what this means is the only things we want in our answer or in our expression are the terms a, b, and c. So we have the identity log of x times y, right? What does that also equal? That also equals, according to the multiplication rule of logarithms, that's also equal to log x plus log y. And what is log x? Log x, according to the question, is a. Log y is b. Therefore, our first answer is going to be a plus b. And we simply repeat the process for each of these identities. However, let's choose some more interesting questions because these questions are quite repetitive. So log x, y over z. So this is going to equal, well, it's going to be log x minus log y, plus log y minus log z. That's just going to be a plus b minus c. And that's our answer for this certain question or a specific question. Now we have log root x, and we're tasked to find that. So, well, what is log root x? That's also equal to log x to the power of 1/2, right? And what logarithm rule can we use? We can use the exponent rule. So now it's going to be 1/2 log x. Therefore, log x is equal to a. Thus, that will imply that this is equal to a over 2. All right, and we can work on some even more examples. So we have log of x squared y to the 7th over the square root of z. So what is this also equal to? Well, we know that this is also equal to, according to the quotient rule, log x squared plus log y to the 7th minus log root z. All right, and we can rewrite this algebraically. So now it's going to be 2 log x plus 7 log y minus 1/2 log z, right? And now we have everything in terms of log x, log y, and log z, and we know our known substitutes for these values. Thus, we can just rewrite it. So now it's going to be 2a plus 7b minus c divided by 2. And this would be our answer for the very last question in the table. Since question 9, 10, and 11 are quite repetitive and exactly the same concept, I would just do one each from 10 and 11. So for question number 10, I would choose ln e to the 2 times x. And we are given that ln x is equal to a, ln y is equal to b, and ln z is equal to c. And we are asked to express the following in terms of a, b, and c, which means all we want is everything to be in terms of a, b, and c, as in those letters should be the only things in the answer, along with any constants that are necessary. So in the question ln e to the power of 2 times x, we can rewrite this according to the multiplication identity, which is just going to be ln e squared plus ln x. And we know that ln e is going to cancel out. The reason is because, well, e to the power of 1 is just always going to equal e. So this is just equal to 1. But before we do that, we must bring down the 2. So it's going to be 2 ln e plus ln x. Therefore, we have simply 2 times 1, which is 2, plus ln x, which apparently is a according to the question. That is going to be our answer, just a plus 2, or 2 plus a. Now for question 11, we are given that log 5 x is equal to a, log 5 y is equal to b, and log base 5 z is equal to c. And we're asked to do the exact same thing, express the following in terms of a, b, and c. So let's express log 25 of x in terms of a, b, and c. Well, what is this? What can this also be equal to? Well, we want to get everything in terms of log 5x, right? Because that's how we're going to get everything in terms of a, b, and c, since these are our equivalents here. So how can we turn the log base to 5? Well, we have 25 here, and we know that that's the same thing as 5 squared. So it's log base 5 squared of x. Now, that's going to also equal to, according to a logarithmic rule, 1/2 log base 5 of x. And what is log base 5 of x? Well, that's equal to a. Therefore, our answer is going to be a over 2. And I chose this in specific because this requires a different log rule that's not very common in the other questions in the table. Moving on to question number 12, we are tasked to solve the following equations involving logarithms. So we have our first question here, which is log base 3 of x plus 1 is equal to 2. So firstly, if we are tasked with solving a logarithmic equation, what we want to do is put everything, we have to make sure the bases are the same if there are multiple logarithms. But for this one, there is only one, so we can simply express this directly as 9 is equal to x plus 1, and this is just taking it in exponential form, so 3 squared is 9 is equal to x plus 1, and we can just solve it. And clearly, x is equal to 8, right? So that's how we solve it with one logarithm. But if there are multiple logarithms, such as question number 15, which involves this, then in question 15, we are given log base 2 of x plus log base 2 of x plus 1 is equal to log base 2 of 6, right? So here we clearly have multiple logarithms in the equation, right? So first things first, we want to make sure all of the bases are exactly the same. And for reference, this is 15a on the IB logarithms problem set worksheet. So if we have log base 2x plus log base 2x plus 1, that means since they have the same bases, and since they are added together, both of these logs, what identity does that give us? That gives us a multiplication identity. So therefore, that's going to equal log base 2 of x and x plus 1 multiplied together inside of the logarithm. And that's going to equal log base 2 of 6. So since we've simplified this into this, and since this stays the same, well, what else do we notice? We notice that on either sides of the equation, we have log base 2 and log base 2. And if both of the bases are equal on either sides of the equation, they simply cancel out. Because mathematically, if you evaluate each of the logs individually, they would still equal the same without the logs in place. Therefore, we would have x squared plus x is equal to 6, and we can subtract that 6 right away. Therefore, factoring it out, since we have a quadratic equation, we have x plus 3 and then x minus 2. And there we go. There you have it. This is in factored form, and possible answers are x is equal to -3 and x is equal to 2. So since we have these two possible answers, well, we have to make sure that these solutions actually work. So as we know, the domain of logarithms is that the x must be greater than 0, always. That is the reason there is a vertical asymptote at 0 for the function log x. And since we can't take a logarithm of a number that's 0 or below or negative, then since this is negative and it's obviously less than 0, we have to cancel out, or we have to scrap this solution out. And x is just equal to 2 for this equation. And this is not the only case where we just cross out a negative number, because let's say we had something such as log base 2 of 2 minus x plus 1, right? Let's just say, let's just make up an example. So let's say let's just solve this quickly. And that's just going to be 2 is equal to 2 minus x. And apparently, if you subtract, that's 0. And then x is just equal to 0 in this case, right? But, so, x is equal to 0 works in this case, right? Because if we do log base 2 of 2 minus 0, that gives us a positive number for what's actually being evaluated inside of the log, and it fulfills the domain for a logarithm. However, if we theoretically get a solution that is larger than 2, for instance, you would get a negative number, right? Or even if the number is actually equal to 2. So this is all theoretical, but if the number is actually equal to 2, then this would imply that, well, inside the logarithm would be negative, right? Therefore, that does not exist. It's not an actual real solution. So you wouldn't choose that solution, even if it's a positive number. If it's greater than something where it creates the inside of the logarithm to be negative, then that causes problems and we have a negative number. So just please keep that in mind. Moving on to question number 17, we are tasked to solve these logarithmic equations, but we must extensively use our logarithmic rules. So we have to use them more extensively. So now I will choose one example, which is going to be C in question number 17. And we are tasked to solve for x in the equation log base 2 x plus 14 is equal to 2 plus log root 2 of x. So in this logarithmic, or in this algebraic equation, we have log base 2 and log root 2. Remember, our goal is to always make the bases equal to each other so we can simplify the logarithm and find out a way to express the expression without any logarithm so we can isolate for x algebraically. So here we have 2 and root 2. How can we rewrite this? Well, we have to use our logarithm rules. So rewriting the expression, we know that root 2 is equal to 2 to the power of 1/2. So just by rewriting it, using our rule for reciprocals, when the base is put to the power of something, that power is going to be brought over to be multiplied here, but it must be the reciprocal of that number. Therefore, it's going to be just like that. And now we have figured out a way to find an expression where all of the logs have the same bases. So now since all of the logs have the same bases, we can combine them. So it's going to be log base 2 of x plus 14 minus 2 log base 2 of x is equal to 2. Now from here, what can we use? Well, we have the quotient rule at our disposal since we have 2 logarithms with the same bases and one is subtracted from the other. Therefore, this is also equal to log base 2 of x plus 14 divided by just x. But mind this, we have a negative 2 here, which is going to be put here. Thus, that's going to be x to the power of 2. Right? So only the 2 is brought up, and that continues to be a subtraction sign. And now that's equal to 2. So what does this give us? Well, now that we have a single logarithm is equal to a constant number, we can just write this as an exponent. So 2 to the power of 2 is equal to 4. And then we've eliminated our logarithm and just rewrote it in exponent form. Now we have x plus 14 divided by x squared is equal to 4. And this looks like a very simple algebraic equation to solve. Now we have 4x squared is going to be equal to x plus 14. Moving everything to one side, we have a quadratic equation. And here we must find two factors. So now we just have to factor this out. So 14 times 4, or negative 14 times 4 is negative 56. Negative 56, that's going to be 4x squared minus 8x. And then here we have 7x minus 14. And now we simply factor out. And then here, common is 7. Now we factored it out. We have 4x plus 7. And we have x minus 2. So our possible theoretical answers are negative 7 over 4, and also x is equal to 2. However, look what we have here. We have a negative number as a possible theoretical answer. Is that possible in a logarithm? Does that fit the domain of a logarithm? No, right? Because that's impossible. You can't take the logarithm of a negative number, and you can test that numerically. Therefore, our only answers should be 2. That's why x is only equal to 2 and nothing else. So this is question C for question 17. So now there is another example on question 17 that requires you to do something similar, where we have log base 4 x plus 14 minus log base 2 of x is equal to 1. So here we have two different bases, right? We have base 4, base 2. We want to get them to be the same. So what can we do? Use the exact same thing we did before. Now we can take out the power of the base of the logarithm, which we want to change, which is going to be 1/2 log base 2 x plus 14 minus log base 2 of x is equal to 1. Now we can put this here according to the power rule for logarithms, which is now going to equal log base 2 of x plus 14, it's the power of 1/2, minus log base 2 x, and that's all equal to 1. So now we must rewrite this as a single logarithm. And is that possible? Yes, it is, because we have a logarithm of two bases on the same side of the equation. One is subtracted from the other. That implies we must use the quotient rule. So we can write this as a single log as x base 2, log base 2, and then x plus 14, square root of that, over x is equal to 1. So now we can write this in exponent form. So now that's just going to be equal to root x plus 14 is equal to x, and that's going to equal 2. So multiplying this out, we have 2x is equal to x plus 14 all square rooted. Squaring both sides, we have 4x squared is equal to x plus 14. And look at what we have here. We can now move everything on one side of the equation. So we have 0 is equal to 4x squared minus x and minus 14. And what do we have here? Well, this was basically the exact same quadratic equation from the last question, so we already know the answer. It's just x is equal to 2, right? If you recall. And just factoring this out, by the way, this would be x minus 2 and something like 7x plus 4 or 4 plus, I don't exactly recall it, but this is the answer for for that. It's the same quadratic equation as the previous question. In question number 18, we're tasked to solve the following equations, but since these are more complicated equations, we must use a substitution. So for question 18, we're given, in part A, we're given ln x everything squared minus ln x squared, subject of x being squared, plus 1 is equal to 0. So it says let x or let y equal ln x, all right? And the reason we're doing this is if we have a complicated equation in general and we want to simplify it, what we can do is let the thing that's making it complicated equal some sort of variable, all right? So in this case, we're just letting ln x equal y because we want to break it up into smaller parts and then at the end, plug ln x back in and then solve it. So substitution is just a technique in algebra where we just want to make something complicated more simple. So that's going to equal y squared minus 2y, and it's 2y because the 2 here goes down due to the rule of exponent for logarithms. So it's going to be 2 ln x, and then since ln x is y, it's going to be 2y plus 1 is equal to 0. And this gives us a quadratic equation where we have y minus 1 squared is equal to 0, and that's after you factored it out, and y is therefore equal to 1. But what is y? Y is ln x. So to solve this, we have ln x is equal to 1. And ln is just log base e. So if we write this as an exponential, all we're doing is evaluating it at this point. So now we have e to the power of 1 is equal to x. Therefore, x is equal to e. So that's our answer for the first part, which is part A. Now, for part B, we're not given information on what should we actually use for the substitute. So, just by looking at it, well, what do we have? We have ln x plus 1 over ln x is equal to 2. What's making it complicated? It's clearly the ln x that's making it complicated, right? So, let y equal ln x for now. You can use any character, doesn't matter. You just want to make it more simple, so you substitute it. So we have y plus 1 over y is equal to 2. And let's move the 2 to one side. Y plus 1 over y minus 2 is equal to 0, right? And now let's expand this. So now we have y squared plus y minus 2y, or not plus y, sorry, plus 1, sorry. And everything is now divided by y. Just find a common denominator, right? So since we have that, that implies that 0 is also equal to y squared minus 2y plus 1. And if we multiply out the y, we just get 0 anyways, so we can disregard that. And it looks like we got the same exact quadratic here. So we already know that y minus 1 squared is now equal to 0, if and only if this expression is true. And now we have ln x is equal to 1, because isolating for y, we just get y is equal to 1, and ln x is equal to y, so therefore ln x is equal to y is equal to 1. Now we have e to the power of 1 is equal to x, which implies x is equal to e. And that's going to be our answer for part B. Now, for part C, we have the equation of log x plus 1 over log x is equal to 2. And remember that it's just base 10 whenever there's nothing at the written for the base. So we have the exact same format, basically. It's just same as ln x plus 1 over ln x is equal to 2, right? Now we have to use an appropriate substitution. What's making it complicated, and how can we simplify it? Well, log x is making it complicated, right? It's just giving us a hard time. So we should probably simplify it, simplify the expression by substituting in y plus y as log x. And that's going to imply that y is going to equal to 1, because we already know the solution for the quadratic equation, right? It's just y is equal to 1. But what is y? Well, I let log x equal y. Therefore, it's going to be log x is equal to 1. And 10 to the power of 1 is just equal to x. Therefore, x is equal to 10. And that's going to be your answer for part C of question 18. So in question number 19, in part A, we are asked to find log base 2 of 32. So part A, find log base 2 of 32. And we know we can write this in exponential form. Well, 2 to the power of a number, which we don't know, right? Let's let that number be x, and then that's equal to 32. We also know that 2 to the power of 5 is equal to 32, just right off the top of your head. So now 2 to the power of x is equal to 2 to the power of 5. That implies that x is equal to 5. And that's your answer for part A. So find log base 2 of 32, that's just 5. Now for part B, we are given that log base 2 of 32 to the power of x over 8 to the power of y can be written as px plus qy. Find the value of p and q. And in this context, p and q are simply constants. The only variables are actually x and y. So if we're asked to find p and q, that implies we're asked to find constants. So how can we do that? Well, firstly, we want to write this entire expression and expand it so we have an expression that actually looks like this, px plus qy. All right. So what can we do? Well, we have two quotients, or we have a quotient inside of the log. Thus, we can use the quotient rule. So it's going to be log base 2, 32 to the power of x, minus log base 2 of 8 to the power of y. And now using the rules of exponent, we can bring down the x. And now we have this. And from here, well, we have, since we've expanded it, and it looks kind of like this, right? Because we have x and then a number, which is log base 2, 32, minus y, and then a number, log base 2, 8. But we want to find the exact values of p and q. How can we do that? Well, since we already have it in this form, basically, just simplify even more. So evaluate each logarithm individually. And off the top of your head, you should know that 2 to the power of 3 is equal to 8. So that's just going to equal 3. And then we have 2 to the power of 5, which we just solved, is equal to 32, because we just evaluated this earlier, right? That's 5. So now what do we have here? We have it in the form 5x minus 3y, right? And although it says px plus qy, well, we have to understand what subtraction actually is. It's simply an addition of a negative number. That's the fact of subtraction. So we can write it as px plus negative 3 times y. Now we have it in this exact form, all right? That is equal to px plus qy. So if that's equal to px plus qy, what does this actually imply? This equality implies that p is equal to 5 and q is equal to negative 3. Therefore, that is our answer right here. P is equal to 5 and q is equal to negative 3. In question number 20, we are asked to express the following in terms of x, y, and z. So we have to express this logarithm in terms of x, y, and z, given that we're letting log p equal x, log q equal y, and log r equal z. So how can we do this? Well, we have a complex logarithm here, right? And we have like multiple terms multiplied and divided inside of it, and everything is squared. So how can we express it so we can have everything in terms of x, y, and z? Well, before we do that, we have to have everything in terms of log p, log q, and log r first, right? And then we can substitute in the values that are given. So how can we do that? Well, firstly, we have to simplify the logarithm and then expand it further. So firstly, well, we have a 2 here, which can, according to the law of exponents, for logarithms, is just equal to that. Just bringing it down, multiply it by the log. It's supposed to be q r cubed. And this is also equal to 2 times, and then according to the quotient rule, we would have log p minus log q minus log r cubed, right? And simply distributing gives us 2 log p minus 2 log q minus, and then here we have the subject of the logarithm, which is r, raised to the power. So according to law of exponent, we have to bring it down. 2 times negative 3 is negative 6. So what have we just done here? Well, we found everything in terms of log p, log q, and log r, right? And expressing the following of anything in general in terms of x, y, and z, if they have corresponding substitutes, requires that the answer must only have x, y, and z, or any constants, in the answer. So if we have log p, log q, and log r, we can just substitute the values in. So now it's just going to be log, or no, just 2 times x minus 2y minus 6z. So now we have expressed this logarithm in terms of x, y, and z given substitutes. And that is our answer. Since question 21 towards 24 is essentially the exact same process as question 20, I will move on to question 25 to avoid repetitiveness. So in question 25, we have the following information. Let log base c of 3 equal p, log base c of 5 equal q, and express these two in terms of p and q for each of the following. So we have log base c of 15 and log base c of 25. So how can we do this? Well, what does this actually mean though? Well, we want to get everything in p and q. So from the previous question, we know that that just means we want to get the final answer in terms of p and q. So only p and q are in the final answer. And we know that we have this information given to us. So what is log base c of 15? Well, what is 15? 15 can also be expressed in as 5 times 3, right? And your strategy for this should be, well, I need everything in terms of log base c of 3 and log base c of 5 first, because those are all corresponding to p and q respectively, right? So before you do anything, we must express it in terms of this first. So what is that also equal to? Well, it's also equal to, according to the multiplication rule, log c base c of 5 plus log base c of 3, right? So now what do we have? Well, since we've expressed it in terms of log c3, log c5, that is therefore equal to p plus q. And that is how we express it. And this is going to be our answer for the first part. Now, for the second part, we have log base c of 25. So how can we express this? Well, what is 25? 25 is also 5 times 5, right? So we can do log base c, 5 times 5. And using the law of multiplication for logarithms, we now just have log base c, 5 plus log base c, 5. So we've expressed everything in terms of either log base c 3 or log base c 5, right? And since we have two of these logarithms, now we just have that equal q. Therefore, since we have two of them, that is now equal to 2q. And this is our final answer. So that is part A completed. Now for part B of question 25, we are asked to find the value of d if log base d of 6 is equal to 1/2. So how can we do this? Well, firstly, we can just rewrite it as an exponent. So that's going to be the square root of d is equal to 6. And now we can just solve this algebraically. So now d is therefore equal to 36. And that is our answer for part B. And we complete part 25. Moving on, in question number 43, we are asked to solve 9 times log base 5x is equal to 25 log x5 expressed in the form 5 to the power of p divided by q such that p and q exist as an integer. So, firstly, solving the equation, we need the bases to be equal, just by thinking algorithmically, right? So, are the bases equal? They're not really equal, right? And can we take out any powers in the bases? Well, not quite, because we have 5 and we have x. So, how can we actually change the bases so that they're equal to each other? Well, if all hope is lost, we can use the change of base formula, which is log b of a is equal to log c of a, and log c is the base that you want it to change to, divided by log c of b. So this implies that for 25 log base x5, we're choosing to do this one, change this base to 5 instead of this, because having a base of 5 is much easier than having a base of x, right? So we can choose to let log 5 of a, and a in this case is 5, and then divided by log 5 of b. b in this case is x, right? So for this part, excluding the 25, this is what we get. And remember, if we have 5 as a base and we also have 5 as what's being evaluated logarithmically, then that's just equal to 1. So now it's just 1 over log base 5x, and that's equal to log x5. All right, so now that we have this, we can plug this into the equation. So all of this implies that 9 log base 5x is equal to 25 divided by log base 5x. And now that we're here, well, how can we solve this equation? Well, this is quite a complicated equation to solve. The reason is because, well, we have we have a log on the denominator, and we have a log on the other side of the equation that's on the numerator, right? So in order to simplify this equation, what should we do? Well, if you want to break things up and make things less complicated, let's y equal the thing that's complicating it, which is log base 5x, because it's just making it more complex. So if we let y equal log base 5x, this is going to imply that this will equal 9y, which is equal to 25 over y. All right, and now that we're here, we can simply solve this algebraically for y. So we have 9y squared minus 25. And as you can see, this gives us a quadratic equation. Since we have a squared term, we have 0 for b, and then we have 25. Negative 25 is a constant. So solving for y, we have to use a quadratic equation, or the quadratic formula, sorry. So we have 0 for b plus minus the square root of 0 squared minus 4 times 9 times negative 25, all divided by 18. And that's going to equal 900 divided by 18, or plus minus the square root of 900, sorry, over 18. And the square root of 900 is simply going to be 30, and then 30 over 18. How can we simplify this? And remember, everything's plus minus, right? Well, if we simplify it further, we can get 5. That's also equal to plus minus 5 over, and then 18 over 3, right? So now, since we have y is equal to plus minus 5 over 3, this is going to imply that we have log base 5x is equal to plus minus 5 divided by 3. So since we now have this, well, now all we have to do is, well, solve for x now, right? And this is easy because we can express it exponentially. So that's going to imply that 5 to the power of 5 over 3 plus minus is equal to x, and that should give us our final answer. 5 to the power of plus minus 5 over 3. And since it told us to find the answer expressed in 5 to the power of p over q, that means p is going to be 5 and q is going to be a 3. And this is therefore our final answer. 5 to the power of plus minus 5 divided by 3. And that is question number 43. So in question number 45, we are tasked to solve the simultaneous equation of 2 to the power of x squared is equal to 4y, or 4 to the power of y, and log base xy is equal to 3 over 2. So since this is a systems of equation, what I'm going to do, or my strategy, will be to solve for one variable first, plug it into this equation, and then get the value for that specific variable, and then plug it back into this equation to find both of the points, x and y, because systems of equations involves two equations where you need to solve for both y and x respectively. So I am going to first use this first equation so I can isolate for y. So that's going to be equal to 2 to the power of x squared, which is equal to 2 to the power of 2y, and that implies that y is equal to x squared over 2, right? And for that, I'm going to plug in x squared over 2 into my equation for log x y is equal to 3 over 2. So now it's going to be log base x, and then we have x squared over 2 is equal to 3 over 2. Now, what is that also equal to? Well, that implies that log x of x squared over 2 equaling 3 over 2, that equality is only true if and only if x to the power of 3 over 2 is equal to x squared over 2. All right, multiplying this out, we have 2x 3 over 2 is equal to x squared. And I just want to solve this equation, so I want to get rid of this 2 because it's a root. So I'm going to square both sides. So now that implies 4x to the power of 3 is equal to x to the power of 4. And since we have this equality now, we can just move this to one side and factor things out. So that also is true if 4x cubed minus x to the fourth is equal to 0. So factoring this out, we're going to have x squared times x cubed, times 4x, and then, just times 4, minus x, and that's going to equal 0. Therefore, we have x is equal to 4, and x is equal to 0. All right? And these are going to be our two main possible solutions. But does 0 work in both of the equations? Well, if x is equal to 0, then that would imply, so yeah, sure, it could work here. But here, log base 0 is simply not possible, right? Because the base has to be bigger, the base has to be bigger than 0. Therefore, because the base has to be bigger than 0 and 0 is a solution, that is not a solution. It's only x is equal to 4. That's the only solution here. So now we have x is equal to 4. That implies that, well, we can just put it in to this equation now. So 2 to the power of 4 squared, is going to be equal to 4 to the y, right? And we can rewrite this as 2 to the 4 squared is equal to 2 to the 2y. And that is going to imply that 4 squared is equal to 2y, and y is going to equal 8. So since we got y is equal to 8 from x is equal to 4, our solution for this question is going to be, therefore, 4, 8. And this is our solution for the simultaneous equation. So in question number 46, we are tasked to do the same thing, just solve for x and y and solve the simultaneous equation. So here I'm going to employ the same strategy, and I'm going to isolate for y first and plug it in here in terms of x. So everything is in terms of x, and then isolate for x and then plug that value into this equation again. So to solve for y first, we're going to manipulate the equation. So we have 2 and then 4x plus 12, no, plus 6, sorry. Yeah. And then that's going to give us y is equal to 4x plus 6, all divided by 3. And from here, we're going to plug this in to the second equation, which is going to be log of base 2, 4x plus 6, all divided by 3. And that's going to equal log base 2 of x and then plus 4. Remember, it's not of x plus 4, it's separated, all right? So now that we're here, so now that we have this equation here, what I'm going to do is I want to combine everything into a single logarithm. And since we have log base 2 here and log base 2 here, that means if we combine them, we can turn them into a single logarithm. So now it's going to be log base 2 of 4x plus 6 divided by 3x, because I simply moved this over, and once you split everything up, this is going to go on the bottom because you're subtracting it, right? And that's going to equal to 4. So once you're here, once you're at 4, now all you need to do is put everything in exponential form. So it's going to be 2 to the power 4 is equal to 4x plus 6 over 3x. And 2 to the power 4 is 16. So 16 times 3 is 48. And that's going to be equal to 4x plus 6 over x. And we have 48. X is equal to 4x plus 6. And that's going to be 44x is equal to 6 divided, and x is going to equal 44, that's going to be 3 over 22. And is x a positive number? And does it work in both equations? Yes, it does. Therefore, it's a valid answer. So now that we've solved for x, we're now going to solve for y. And since we already know x, all we need to do is plug it in to an equation to solve for y. So I have the equation here that can be rewritten. So y is going to equal 4 times 3 over 22 plus 6, all divided by 3. And that's going to be 12 over 22. 12 over 22 is going to be added to 6 over 3. And we already know that this is going to be 6 over 11 plus 6. And then put in an 11 here. That's going to equal 66 plus 6 over 11, which is, as we know, this is just arithmetic now, but this in general is our y value. So I'm just going to plug this into my calculator. And then that should equal 24 over 11. Assuming that these are all divided by 3. And once you're done simplifying, your answer is going to equal 24 over 11. So if this is your x and this is your y, the way you would write your answer is x, y is equal to 3 over 22. and 24/11. And this is therefore your final answer for the simultaneous equation in question number 46. Now moving on to part C, we're just asked to calculate the infinite sum now. So it's the same sequence as part B, but it's the infinite sum, so we just use the infinite sum formula for a geometric series, which is a sub 1 divided by 1 minus r. We already know that. First term is ln2, the common ratio is ln2, so we just plug it in, and this is our answer for part C. So now moving on to question number 49. In part A, we're asked to find the sum of the series ln2 plus ln2 squared plus ln2 cubed, so on and so forth, up until ln2 to the power of 10. So since we know if we bring down all the powers, we're just going to get ln2 plus 2ln2 plus 3ln2 plus 4ln2, and so on until we get to 10ln2. And this implies that this is an arithmetic series. So we should use the formula for an arithmetic series to solve for the sum. So S sub n is going to equal n, which is the number of terms, a1 plus an, all divided by 2. And that's just going to imply that Sn, or the sum, is going to equal 10/2 multiplied by a1, which is going to be ln2, plus an, which is going to be 10 ln2. And that's me already using the exponent rule. So that's going to equal 5 times 5 ln2 plus 10 ln2. And now distributing it, we simply get, 5 and then 50. 50 plus 5 is 55. Therefore, this is what our answer will be. That's equal to S sub n, which is equal to the sum of part A for number 49. Now, in part B of question number 49, we're asked to calculate another sum where it's ln2 plus ln2 everything squared plus ln2 everything cubed, so on and so forth until we get to the 10th term. And this implies that the power in the sequence is rising every single time. So calculating the sum means that we have to find the geometric series. So since a geometric series, its formula is going to be S sub n is equal to a times Rn minus 1, all divided by r minus 1. We know that a, or a sub 1, is the first term. We can just plug this into the formula, and that's going to equal ln2 times r to the power of n. And what is the common ratio here? Well, if we divide, for example, just ln2 everything to the power of 3 divided by ln2 everything to the power of 2, 3 minus 2 just by exponent rules is just 1, so the common ratio has to be ln2. So it's going to be 1 minus ln2 to the 10th power, because it's the 10th term that we're trying to calculate the sum of. Therefore, it's going to be this fraction all divided by 1 minus ln2. And once we're here, this is essentially our expression for the sum of the first 10 terms. Moving on to question number 50, we are tasked to compute this sum here in the form a ln2 such that a exists as a rational number. So since we have a sum here, and since we understand that this is an arithmetic series because it is 2 to the power of r, and bringing that down, visualizing the sequence, it's an arithmetic series. So we can use the formula for an arithmetic series. And we're going to use this one. a1 plus a over n, a sub n divided by 2. So that's going to imply that the sum is going to equal n, which is going to be the amount of terms, which is 50 over 2, times a1, which is ln2r, plus a to the n, which is going to be ln2 50, and that's supposed to be 1. So now that we have that, we just simplify even more. So S sub n is going to equal 25 ln2 plus 25 ln2 to the power of 50. And we know that we can bring this down. So 50 times 25 is equal to 1250. 1250 ln2. And we know that we have 25 ln2. And we can just now add this together. And that is going to equal 1275 ln2. And that's how we calculate this sum for question number 50.